The contemporary civilian experience is defined by a seamless, invisible web of technologies that facilitate instantaneous communication, precise geolocation, and ubiquitous computing. A teenager in Seoul navigates to a coffee shop using a smartphone. A logistics manager in Hamburg tracks a container ship across the Atlantic. A farmer in Iowa monitors soil moisture via satellite uplink. These actions, mundane in their modern frequency, are the downstream consequences of a high-stakes existential struggle for survival that dominated the latter half of the 20th century. They are the peace dividends of the Cold War. The invisible arms race, a competition not merely of yield and tonnage, but of precision, miniaturization, and survivability, served as the primary engine for the information age. While the narrative of Silicon Valley often champions the garage entrepreneur and the venture capitalist as the titans of innovation, the historical record suggests a different protagonist: the military-industrial complex of the United States, driven by the specific strategic requirements of nuclear deterrence. The trajectory of this innovation was not linear, nor was it purely commercially motivated. It was shaped by specific tyrannies: the tyranny of numbers in avionics, the tyranny of distance in submarine warfare, and the tyranny of vulnerability in command and control. To solve these problems, the United States Department of Defense and its associated agencies, DARPA, NASA, and the Navy, functioned as the market maker of first resort, absorbing the exorbitant research and development costs of technologies that had no immediate commercial viability. This analysis explores the genealogy of foundational pillars of modern society. Let's begin with the integrated circuit, the global interworking, satellite navigation, and intelligent autonomous systems. By tracing these technologies from their classified origins in the Minuteman missile silos and the corridors of the Pentagon to their ubiquity in consumer electronics, we reveal a consistent pattern. The military requirement for 5 nines reliability, 99.999%, and operation in harsh environments created the necessary economic and technical substrate for the information age. Furthermore, we examined the parallel, often less successful efforts of the Soviet Union, illustrating how the specific, decentralized nature of American military procurement fostered an ecosystem that could eventually transition from defense to commerce. A transition that ultimately defined the victor of the Cold War, not by the missiles fired, but by the economies built.
The Silicon Foundation, the tyranny of numbers, and the integrated circuit. The integrated circuit, IC, the microscopic city of transistors that powers everything from toasters to supercomputers, is often viewed through the lens of Moore's law, a seemingly natural progression of doubling capability. However, the initial spark that ignited this exponential growth was not consumer demand, but a crisis in ballistic missile guidance known as the tyranny of numbers. In the late 1950s, the strategic balance of power relied on the Intercontinental Ballistic Missile, ICBM. These delivery systems required sophisticated onboard computers to calculate trajectories, compensate for wind shear, and ensure the payload reached its target. The existing technology, based on vacuum tubes, was woefully inadequate for this task. Tubes were fragile, generated immense heat, and consumed vast amounts of power. The invention of the transistor was a significant leap forward, but it introduced a new problem. As missile systems grew more complex, the number of discrete components, transistors, resistors, capacitors, exploded. A guidance system might require tens of thousands of individual parts, each hand-soldered into a circuit. This gave rise to the tyranny of numbers. As the component count increased, the statistical probability of a system-wide failure approached certainty. If a system had 100,000 parts and each part was 99.9% reliable, the system itself would almost certainly fail. For the U.S. Air Force, this was an unacceptable strategic vulnerability. A missile that failed on the launch pad or veered off course due to a loose solder joint was a missile that failed to deter a Soviet strike. The solution appeared in 1958-1959 when Jack Kilby of Texas Instruments and Robert Noyce of Fairchild Semiconductor independently developed the integrated circuit. By fabricating multiple components on a single chip of semiconductor material, they theoretically solved the interconnection problem.
Despite the promise of the integrated circuits, the commercial electronics industry remained skeptical. The early chips were slow, untested, and astronomically expensive. In 1962, a single integrated circuit cost approximately $50 unadjusted, a price point that made them laughable for use in consumer radios or televisions. The yield rates, the percentage of chips that actually worked after manufacturing, were pitifully low. The turning point came with the Minuteman II missile program. The Air Force needed to increase the range of the Minuteman missile to reach more targets within the Soviet Union. Developing a new propulsion system would have been a costly, multi-year endeavor. The alternative was to reduce the weight of the payload. The Autonomy division of North American Aviation, the prime contractor, proposed a radical solution. Replace the discrete transistor computer with one built from the new, unproven integrated circuits. This decision fundamentally altered the economics of the semiconductor industry. In 1962, the Department of Defense market for monolithic integrated circuits was effectively 100% of total U.S. production. By committing to the Minuteman II, the Air Force became the first customer that the industry desperately needed. This volume of procurement allowed manufacturers like Texas Instruments, Fairchild, and Westinghouse to invest in better production equipment and refine their lithography processes. The results were dramatic. The Minuteman II guidance computer achieved a 50% reduction in weight compared to its predecessor, directly translating to increased range. More importantly, the reliability skyrocketed. The mean time between failures for these new systems proved that the tyranny of numbers could be defeated. The massive injection of military capital drove the price of an IC down from $50 to just over $2 by 1968. This aggressive cost curve, subsidized entirely by the taxpayer for the sake of nuclear deterrence, was what eventually made it economically feasible for companies to put chips in calculators, watches, and eventually personal computers.
While the Air Force drove the volume, NASA's Apollo program drove the complexity. The Apollo Guidance Computer, AGC, designed by the MIT Instrumentation Laboratory, was the first digital computer to use ICs for its logic operations. Unlike the Minuteman, which needed to guide a warhead for 30 minutes, the AGC had to function flawlessly for weeks in deep space, with no possibility of repair. The decision to use ICs was a calculated risk. The MIT designers used 4100 Type G 3-input NOR gate circuits for the Block I computer. This standardization, using thousands of identical simple chips rather than fewer complex specialized ones, was a strategy to ensure reliability. If one type of chip was thoroughly tested, the probability of success increased. The Apollo program also introduced the concept of digital redundancy in a way that foreshadowed modern fault-tolerant computing. The lunar module, LM, carried a primary guidance system, but also a backup, the Abort Guidance System, AGS. Built by TRW, the AGS was a strapped-down analytic system that could autonomously pilot the LM back to the command module if the primary computer failed. It was, in essence, a dedicated emergency computer, a philosophy of redundancy that persists in modern avionics and critical infrastructure. The military's influence on computing did not end with the moon landings. By the late 1970s, the complexity of chips was growing so fast that designing them was becoming a bottleneck. In response, DARPA, Defense Advanced Research Projects Agency, launched the Very Large-Scale Integration (VLSI) program. The VLSI program, managed by luminaries like Robert Kahn and Conway, sought to separate the design of a chip from its fabrication. This led to the Meade and Conway Revolution, which established standardized design rules that allowed students and researchers to design complex chips without needing to own a billion-dollar fabrication plant. To facilitate this, DARPA funded the establishment of MOSIS, Metal Oxide Silicon Implementation Service, in 1981. MOSIS acted as a multi-project wafer service, aggregating designs from various universities, Stanford, Berkeley, MIT, onto a single silicon wafer, dramatically lowering the cost of prototyping. This program directly funded the research that led to the Reduced Instruction Set Computer, RISC. Projects like the Berkeley RISC and the Stanford MIPS, microprocessor without interlocked pipeline stages, were funded by DARPA to create more efficient processors for military applications. These academic projects evolved directly into the commercial SPARC and MIPS architectures that powered the workstation boom of the 1980s and 90s, Sun Microsystems, Silicon Graphics. The graphics engines developed under these grants eventually laid the groundwork for the GPUs that today power everything from video games to artificial intelligence training clusters. It is instructive to compare the American trajectory with that of the Soviet Union. While the U.S. military relied on a merchant model, funding private companies like TI and Fairchild, who competed for contracts, the Soviet approach was top-down and state-controlled. Intelligence reports from the era indicate that while the Minuteman III was utilizing sophisticated integrated circuits for its MIRV, multiple independently targetable re-entry vehicle, systems, Soviet missiles were often still relying on miniaturized vacuum tubes or discrete transistors. The Soviets lagged significantly in the processing know-how and quality control required for IC mass production. The CIA assessed that the transfer of U.S. semiconductor technology to the USSR would have accelerated the transition to IC-based guidance systems, a capability the Soviets struggled to develop indigenously. This technological gap in microelectronics became a defining factor in the later stages of the Cold War, as American smart weapons outclassed Soviet hardware in terms of precision and processing power.
Nets of survival: the myth and reality of the Internet's origin. Few technologies are as mythologized as the Internet. The popular narrative suggests that the ARPANET was explicitly built to survive a nuclear war, a cockroach of a network designed to function in the radioactive ruins of the United States. The reality, revealed through the archives of the RAND Corporation and ARPA, is a tale of two distinct threads of innovation that converged to create the modern packet-switched world. In the early 1960s, the RAND Corporation, a think tank dedicated to military strategy, faced a terrifying logistical problem. The U.S. command and control infrastructure relied on the AT&T telephone network. This network was centralized. Calls were routed through hierarchical switching centers. A Soviet nuclear strike that took out a few key hubs could decapitate the nation's leadership, preventing the president from ordering a counterstrike. Paul Barron, a researcher at RAND, proposed a radical alternative: distributed communications. Instead of a star topology, centralized, he envisioned a mesh network, a fishnet where every node was connected to several neighbors. If a node was vaporized, the information would simply flow around the damage. To make this work, Barron invented the concept of chopping data into message blocks,
later called packets, and using hot potato routing. Each node would pass the packet to the next available node as quickly as possible, ensuring no single point of failure could stop the message. Barron's work was explicitly focused on nuclear survivability. His 1964 papers on distributed communications detailed a network that could withstand heavy damage. However, the AT&T engineers of the time dismissed his ideas as impractical, and the system was never built by the Air Force as originally envisioned. Simultaneously, at ARPA, J.C.R. Licklider and Robert Taylor were facing a different problem. They were funding computer research at universities across the country, but these computers were incompatible and isolated. If a researcher in Utah wanted to use a program on a computer in Massachusetts, they couldn't. ARPA was spending millions buying redundant mainframe computers for different sites. Taylor and Larry Roberts conceived of a network not for nuclear survival, but for resource sharing, allowing a user at one terminal to log into a remote computer and use its processing power. This was an economic efficiency measure. When Roberts began designing the ARPANET in 1967, he needed a method to move data efficiently. Circuit switching, the telephone method, was inefficient for bursty computer data. He adopted the packet switching concepts developed by Donald Davies at the National Physical Laboratory in the UK, who had independently discovered the same principles as Barron and integrated Barron's routing concepts.
The myth of the nuclear internet arises from the conflation of these two threads. ARPANET was not built to survive a bomb. It was built to share calculators. However, the technology chosen to achieve this, packet switching and distributed routing, happened to be the same technology Barron designed for survivability. The robustness that allows the modern internet to route around a severed undersea cable or a power outage is a direct genetic inheritance from Barron's Cold War paranoia, even if the ARPANET's funding justification was civilian resource sharing. The early ARPANET relied on a protocol called the Network Control Program, NCP. As the network grew to include satellite links, SatNet, and radio networks, PRNet, NCP proved inadequate. It couldn't handle a network of networks. Vinton Cerf and Robert Kahn developed a new suite of protocols, TCP/IP, designed to be rugged and flexible. The transition to TCP/IP was not gradual. The Defense Communications Agency mandated a Flag Day. On January 1, 1983, every machine on the ARPANET was required to switch to TCP/IP simultaneously. Machines that didn't switch were cut off. This massive, coordinated logistical feat, unimaginable in a purely commercial market of competitors, established the universal language of the modern Internet. Ron Brosma, a researcher at the Naval Undersea Center operating Node No. 3, recalled the transition. The old IMP, interface message processor, addresses were limited to 256 hosts, a ceiling that seems absurd today, but was a hard limit of the 8-bit addressing scheme. The switch to TCP/IP opened the address space, allowing the network to expand exponentially. This Flag Day is widely considered the true birthday of the modern Internet, a moment where military fiat imposed the standardization necessary for global scale.
The clock in the sky, geopolitics, and the birth of GPS. If the Internet is the nervous system of the modern world, the Global Positioning System, GPS, is its vestibular system, providing the sense of balance and orientation. Like the Internet, its origins are naval and nuclear, born from the need to aim missiles from the middle of the ocean. The story begins with Sputnik,
Researchers at the Applied Physics Laboratory, APL, at Johns Hopkins realized they could track the Soviet satellite by analyzing the Doppler shift of its radio signal. This led to the inverse realization: if the satellite's orbit was known, a receiver on Earth could calculate its own position. This was a revelation for the Navy. The Navy was developing the Polaris submarine-launched ballistic missile. To launch a missile accurately, a submarine needed to know its own location precisely. In the featureless expanse of the ocean, submerged for weeks, traditional navigation was impossible. The Navy developed Transit, the first satellite navigation system. Transit, operational in the 1960s, was a Doppler-based system. It was effective, but had severe limitations. It was a two-dimensional system, latitude and longitude only, and it was slow. A submarine had to wait for one of the 6 satellites to pass overhead, which could take hours to get a fix. For a fast-moving aircraft or a missile in flight, transit was useless. To solve the problem of continuous instantaneous 3D navigation, the Naval Research Laboratory, NRL, initiated the TIMation, Time Navigation Program. The concept was simple physics. Distance equals rate times time. If you know the speed of light and the exact time a signal left a satellite, you can calculate your distance from it. If you measure the distance to multiple satellites, you can triangulate your position. The challenge was the clock. To get 10-meter accuracy, the clock needed to be accurate to within 30 nanoseconds. Quartz clocks were not stable enough. The TIMation program championed the use of atomic clocks in space. TIMation 1, launched in 1967, and TIMation 2, 1969, proved that crystal oscillators could work, but TIMation 3, NTS-1, 1974, was the first to fly a rubidium atomic clock, followed by NTS-2 with a cesium clock. This Naval Research Foundation was pioneering. It proved that sensitive atomic clocks could survive the rigors of launch and the radiation of space. This technology allowed the GPS architecture to replace the heavy, expensive clocks in the satellites, allowing the receivers on the ground to be small, cheap, and passive, a critical design decision that eventually allowed GPS chips to fit into smartphones.
In 1973, the Department of Defense forced a marriage between the Navy's TIMation program and the Air Force's Project 621B, which had developed the signal structure. The result was Navstar GPS. The system architecture called for a constellation of 24 satellites, ensuring that at least 4 were visible from any point on Earth. The inclusion of the 4th satellite was a brilliant mathematical hack. 3 satellites are sufficient for 3D geometry, but only if the receiver's clock is perfectly synchronized with the satellite clocks. By adding a 4th satellite, the system could solve for 4 variables, namely X, Y, Z, and time bias, allowing the receiver to use a cheap quartz clock and mathematically correct its time to match the atomic clocks in space. The Soviet Union paralleled this development with GLONASS. Development began in 1976, with the system declared operational in 1993. A key difference lies in the orbital mechanics. GLONASS satellites orbit at a higher inclination, 64.8 degrees, compared to GPS, around 55 degrees. This makes GLONASS significantly more effective at high latitudes, critical for the Soviet Union, whose territory extends into the Arctic. However, the economic collapse of the Soviet Union took a toll. By the late 1990s, the GLONASS constellation had degraded significantly due to a lack of replacement launches, leaving huge gaps in coverage. It was only restored to full capability in the 2010s. This contrast highlights how the economic engine supporting the U.S. military and its eventual integration with the civilian market ensured the longevity of GPS. The transition of GPS from a military secret to a global utility was driven by tragedy and economics. After Korean Airlines Flight 007 strayed into Soviet airspace due to a navigational error and was shot down, President Reagan issued a directive making GPS available for civilian use to improve aviation safety. The DoD remained wary of enemies using GPS for precision strikes. They implemented selective availability, intentionally introducing errors into the civilian signal, limiting accuracy to about 100 meters. By the late 1990s, the commercial pressure was immense. Industries from shipping to surveying needed better accuracy. On May 1, 2000, President Clinton ordered selective availability turned off. Civilian accuracy improved tenfold overnight, from 10 meters to 10 meters. The price of GPS receiver chips plummeted from $3,000 to $1.50 as volumes exploded. This decision paved the way for the modern app economy. Uber, Google Maps, and Tinder are all downstream effects of this policy change.
The hidden signals, wireless, CDMA, and the legacy of stealth. The modern smartphone's ability to make a call in a crowded stadium without interference is based on a technology designed to be unjammable and invisible: spread spectrum. In one of the most unlikely partnerships in history, Hollywood actress Hedy Lamarr and avant-garde composer George Ann Tile patented a secret communications system in 1942. They recognized that radio-controlled torpedoes were vulnerable to jamming. If the enemy found the frequency, they could flood it with noise. Lamarr and Ann Tile proposed frequency hopping. Instead of broadcasting on a single channel, the transmitter and receiver would hop together across 88 different frequencies, matching the keys on a piano, in a synchronized pattern. To an outsider, the signal would look like random noise. The U.S. Navy initially rejected the patent, finding the mechanical player piano mechanism impractical for a torpedo. However, the concept was resurrected in the 1950s with the advent of transistors. By the 1962 Cuban Missile Crisis, the Navy was using frequency-hopping radios to maintain secure communications that Soviet surveillance ships could not intercept. While frequency hopping secured the signal, digital communication required a way to correct errors caused by static and interference. In 1967, Andrew Viterbi, a researcher and professor, published the Viterbi algorithm. This was a mathematical method for decoding convolutional codes. It essentially allowed a receiver to guess the most likely message sent, even if the signal was heavily corrupted. The algorithm found its first major application in deep space telemetry. NASA probes like Voyager, transmitting faint signals from billions of miles away, relied on Viterbi decoding to reconstruct the images of Jupiter and Saturn from the background radiation of space. In the late 1980s, the cellular industry was looking for a way to increase capacity. Viterbi, having co-founded Qualcomm, proposed using military-grade spread spectrum technology for cellular networks. He championed CDMA, Code Division Multiple Access. Unlike the existing standards, which divided calls by time, TDMA, or frequency, FDMA, CDMA allowed every phone to transmit on the same frequency at the same time. Each call was assigned a unique code, a pseudo-random sequence. The receiver used Viterbi's algorithms to filter out the noise of other calls and reconstruct the specific conversation. This technology, derived directly from anti-jamming military radios and deep space probes, became the dominant standard for 3G networks and the foundation of modern mobile data. It is also worth noting the U.S. Army's role in tactical cellular. In the 1980s, the Army deployed Mobile Subscriber Equipment, MSE. This was, effectively, a mobile cellular network that allowed soldiers to communicate while moving in vehicles. It automated call routing and switching in a way that mirrored the civilian cellular networks being built simultaneously. The research into robust mobile handoffs for MSE directly informed the standards used in civilian infrastructure.
The Sensing World, MEMS, and the Democratization of Guidance. The modern smartphone is a sensor platform. It knows when it is tilted, when it is moving, and which way is north. These capabilities utilize micro-electro-mechanical systems, MEMS, tiny machines etched into silicon.
These sensors are the great-grandchildren of the massive guidance units used in ICBMs. In the 1960s, measuring acceleration required a device the size of a soup can, costing thousands of dollars. The Titan II missile and the Apollo spacecraft used these electromechanical accelerometers for inertial navigation. They were precision instruments, critical for ensuring a nuclear warhead landed on a silo and not a city. The drive to miniaturize these systems for smaller tactical munitions led DARPA and the Army's Diamond Ordnance Fuse Laboratories to fund research into MEMS. They sought to use the same lithography techniques used for chips to etch mechanical beams and gears onto silicon. The breakthrough for civilian application came not from phones but cars. In the 1990s, the automotive industry adopted MEMS accelerometers for airbag deployment. The old mechanical switches were unreliable. MEMS chips were precise and cheap. This mass production for the auto industry lowered the cost of accelerometers from hundreds of dollars to pennies. Once the price dropped, they migrated to consumer electronics, enabling the screen rotation feature of the first iPhone and the motion controls of the Nintendo Wii. The legacy of DSP. The term DSP carries a dual legacy. In the Cold War, it stood for the Defense Support Program, a constellation of satellites equipped with infrared sensors to detect the heat bloom of Soviet missile launches. To process the data from these satellites and from the vast networks of anti-submarine hydrophones, the military developed Digital Signal Processing (DSP) chips. These chips were designed to perform rapid mathematical operations, fast Fourier transforms, to filter noise from signal. Today, DSP chips are the engines of multimedia. When a smartphone compresses a voice for a call, or decodes an MP3 file, or processes a JPEG image, it is using the same mathematical architecture originally designed to find a distinct Soviet submarine propeller sound in a noisy ocean.
The artificial mind, CALO, DARPA, and the road to autonomy. The final layer of the modern technology stack is intelligence, the ability of software to understand speech, predict intent, and navigate the physical world. This field, now dominated by Silicon Valley giants, has its roots deeply embedded in DARPA's attempts to solve the cognitive overload of the modern battlefield. In 2003, facing a military environment drowning in data, DARPA launched the PAL program, the Perceptive Assistant That Learns. The goal was to create a cognitive software assistant that could learn from its user and organize information autonomously. The flagship project was CALO, Cognitive Assistant That Learns and Organizes, led by SRI International. CALO was a massive multi-university effort involving over 300 researchers. It focused on natural language processing, machine learning, and ontology. The system was designed to help military commanders schedule meetings, sort emails, and prepare briefings. The technology developed under CALO was too valuable to remain in the lab. SRI International spun off a startup named Siri Inc. in 2007. The startup commercialized the voice recognition and intent prediction engines developed for the Pentagon. In 2010, Apple acquired Siri, and in 2011, it was integrated into the iPhone 4S. The cheerful voice that helps a user bake a cake was born from a military requirement to help a general manage a war. The current revolution in autonomous vehicles can be traced to a specific date, March 13, 2004. Congress had mandated that 1/3 of all operational ground combat vehicles be unmanned by 2015 to reduce casualties from IEDs and ambushes. To accelerate this, DARPA held the grand challenge, offering a $1 million prize to any team that could build a car to drive autonomously across 142 miles of the Mojave Desert. The 2004 event was a disaster. No car finished, and the furthest anyone got was 7.5 miles. But it galvanized the research community.
DARPA doubled the prize to $2 million for the 2005 challenge. This time, 5 vehicles finished the course, led by Stanley from Stanford University. The legacy of this event is direct. The team leaders from the Stanford and Carnegie Mellon teams, Sebastian Thrun and Chris Urmson, were hired by Google to start their self-driving car project, which eventually became Waymo. The sensor fusion, LiDAR processing, and path planning algorithms developed to keep military supply trucks safe are now the intellectual property underpinning the entire autonomous driving industry.
The narrative of the invisible arms race reveals a technological paradox. The Cold War was a period of immense fear, where two superpowers prepared diligently for the end of the world. Yet the specific technical requirements of that preparation, the need for a missile to guide itself, for a network to survive a bomb, for a radio to be unjammable, created the building blocks of the modern digital economy. The peace dividend was not merely the reduction of defense budgets in the 1990s, but the repurposing of these survival tools for connectivity and commerce. The Minuteman's brain became the microprocessor in our laptops. The Navy's timekeeper became the navigation system for our Uber rides. RAND's nuclear shield became the social network. The torpedo's secret code became the 5G network. The general's digital aid became the voice assistant in our pockets. This history challenges the notion that government and military spending crowds out innovation. Instead, it suggests a model where the state acts as the risk absorber of first resort, tackling problems too expensive or too long-term for the free market to touch. The iPhone is not just a product of Cupertino. It is a pocket-sized museum of the Cold War, a testament to how the technologies of death were successfully beaten into the plowshares of the digital age. The challenge for the 21st century will be whether the civilian innovation engine, now self-sustaining, can continue to produce such fundamental breakthroughs without the existential pressure of a global conflict to drive them.
Now let's dive into the legacy of Cold War space race. The invisible mesh, the evolution of satellite communications. The architecture of the modern information age was conceived in the speculative intersection of radar engineering and science fiction, long before it became a geopolitical necessity. The concept of the geostationary orbit, a specific altitude of 42,164 kilometers from the Earth's center, where a satellite's orbital period matches the planet's rotation, was first proposed by Arthur C. Clarke in a 1945 letter to Wireless World titled Extraterrestrial Relays. Clarke, drawing on his wartime experience with radar, envisioned a trio of space stations that could act as global relays, a concept that was technically sound but operationally impossible at the time. It required the catalytic pressure of the Cold War to transform this theoretical construct into a strategic imperative. The theoretical era ended abruptly on October 4, 1957. The launch of Sputnik 1 by the Soviet Union did not merely inaugurate the space age, it shattered the American illusion of continental invulnerability. A polished metal sphere, 58 centimeters in diameter and equipped with 4 external radio antennas, Sputnik was a simple beacon, transmitting a beep-beep signal that could be heard by amateur radio operators worldwide. While militarily benign, its passage over the United States demonstrated that the Soviet Union possessed the rocketry capable of delivering nuclear warheads across intercontinental distances. The American response was immediate and multifaceted, driving the rapid development of communication satellites not just for prestige, but for command and control. The first American answer came in 1958 with Project SCORE, signal communications by orbiting relay equipment. Launched aboard an Atlas rocket, SCORE was the world's first communication satellite, broadcasting a pre-recorded Christmas message from President Dwight Eisenhower to the world. This mission proved that active voice transmission from orbit was feasible,
moving beyond the passive reflection concepts initially explored. The early 1960s saw a rapid diversification of satellite architecture. Project Echo in 1960 utilized massive metallicized balloon satellites acting as passive reflectors, bouncing signals from one ground station to another. However, the future lay in active repeater satellites. Courier 1B in 1960, the world's first active repeater satellite, demonstrated the ability to store and forward teletype messages at high speeds. This technology was the precursor to modern email and packet switching, developed initially to ensure that military orders could be transmitted even if real-time links were severed. The maturation of this technology arrived with Telstar 1 in 1962. A collaboration between NASA and AT&T, Telstar was the first satellite to facilitate active transatlantic communications, transmitting the first live television images between the United States and France. This was followed closely by SYNCOM-2 in 1963, the first satellite to achieve the geosynchronous orbit Clark had predicted, and SYNCOM-3 in 1964, which achieved the true geostationary orbit, allowing it to beam live coverage of the 1964 Tokyo Olympics to viewers in the United States.
As the technical feasibility of satellite communications became undeniable, the United States faced a complex policy challenge: how to organize this new domain. The debate centered on whether satellite communications should be a government monopoly, an extension of existing telecommunications giants like AT&T, or a new entity entirely. The resolution was the Communications Satellite Act of 1962, signed by President John F. Kennedy. This legislation was a landmark in the history of space law and industrial policy. It declared that it was the policy of the United States to establish, as expeditiously as practicable, a commercial communications satellite system. The act was a compromise born of antitrust concerns. Congress feared that allowing a single carrier like AT&T to dominate space communications would stifle innovation and competition. Consequently, the act created the Communications Satellite Corporation, ComSat, a private company subject to government regulation, which would serve as the U.S. signatory to the international consortium Intelsat. This legislative framework had profound implications. It mandated that the benefits of this new technology be reflected in both quality of services and charges, and explicitly stated that the system should serve the needs of economically less developed countries. This effectively bifurcated the development of space communications. A civilian track, led by ComSat, Intelsat, focused on global commerce and telephony, and a military track, focused on secure, survivable command and control.
While the civilian world celebrated the global village enabled by Intelsat, the Department of Defense was constructing a parallel, shadowed infrastructure designed to survive World War III. The limitations of high-frequency radio, which relied on bouncing signals off the ionosphere, were starkly apparent. HF was susceptible to solar interference, atmospheric disturbances, and, crucially, nuclear effects. A high-altitude nuclear detonation could disrupt the ionosphere, severing communications with strategic forces at the precise moment they were needed most. The military's answer began with the initial Defense Communications Satellite Program, IDC-SP. Launched between 1966 and 1968, these satellites were relatively simple, spin-stabilized spheres, launched in clusters to form a random ring around the equator. They lacked station-keeping thrusters, meaning ground stations had to track them as they drifted. Despite their simplicity, they provided the first reliable high-capacity links for military operations, particularly supporting the war effort in Vietnam, by carrying high-speed digital data and high-quality voice channels that HF radio could not support. The evolution to the Defense Satellite Communications System, DSCS-2, in 1971, marked a quantum leap in capability. These satellites were three-axis stabilized, allowing for higher gain antennas and focused spot beams that could be directed at specific theaters of operation.
Crucially, they introduced increased privacy and compatibility with portable ground units, allowing tactical commanders to access strategic networks. However, the defining characteristic of Cold War military SATCOM was survivability. The DSCS-3 generation, which entered development in 1975, was designed as a digital fortress. These satellites were hardened against the electromagnetic pulse, EMP, of nuclear weapons and featured advanced anti-jamming capabilities. They utilized multi-beam antennas that could null jamming signals, effectively ignoring energy coming from a hostile jammer while continuing to receive friendly communications. This military investment in jam-resistant waveforms, phased array antennas, and radiation-hardened electronics laid the groundwork for the reliability protocols used in modern banking networks and secure corporate communications. The requirement to communicate through the noise of electronic warfare birthed the error correction codes that today ensure the integrity of digital transactions.
By the 1980s, the civilian satellite infrastructure, built upon the foundation of the 1962 Act, had matured to the point where it began to influence the geopolitical landscape itself. This phenomenon, termed teleplomacy, was driven by the rise of 24-hour news networks, most notably cable news network CNN. The ability to transmit live video from anywhere on Earth using portable satellite uplinks fundamentally altered the decision-making cycle of governments. Diplomatic cables, which traveled through bureaucratic channels, were outpaced by live broadcasts. During the student protests in Beijing, the presence of satellite uplinks allowed Western media, including CBS and CNN, to broadcast live from the square. When the Chinese government imposed a crackdown, the images were beamed instantly to a global audience. The CNN effect meant that the world was watching in real time, creating immense diplomatic pressure that traditional statecraft could not contain. In November 1989, NBC's Tom Brokaw reported live from the Brandenburg Gate as the Berlin Wall fell. This was not merely news reporting, it was a shared global experience enabled by the satellite network. The visual confirmation of the wall's demise, transmitted instantly, accelerated the collapse of the Eastern Bloc regimes as citizens in other Warsaw Pact nations watched the events unfold live. The zenith of this era was the Gulf War. Iraqi President Saddam Hussein, understanding the power of the medium, allowed CNN to retain a dedicated phone line and satellite link, even as other journalists were expelled. As the air war began, CNN reporters Peter Arnett and Bernard Shaw broadcast the anti-aircraft fire over Baghdad. This exclusive link meant that military commanders and the public were watching the same feed. The war was consumed as a real-time global event.
The most sophisticated evolution of Cold War space architecture, however, is found in the current race for low Earth orbit mega-constellations. The lineage of systems like SpaceX's Starlink can be traced directly to the Strategic Defense Initiative, or SDI, President Reagan's controversial 1983 proposal to build a shield against ballistic missiles. In the late 1980s, the Strategic Defense Initiative Organization, or SDIO, pivoted from large, laser-wielding battle stations to a concept known as brilliant pebbles. This architecture envisioned a constellation of thousands of small, autonomous interceptor satellites orbiting in LEO. The premise was that a dispersed cloud of sensors and kinetic kill vehicles could detect and intercept Soviet ICBMs in their boost phase, making the system resilient against attack due to the sheer number of targets. The technical requirements for brilliant pebbles were formidable and, at the time, revolutionary. Satellites had to be cheap and manufactured on an assembly line, a radical departure from the bespoke, hand-built nature of traditional spacecraft. The system had to detect, track, and engage targets without human intervention due to the short flight times of missiles. The satellites needed to communicate with one another, inter-satellite links, to hand off tracking data as missiles traversed the horizon. Although Brilliant Pebbles was canceled in the early 1990s following the end of the Cold War, the intellectual capital and technological blueprints survived. The concept of a proliferated LEO constellation became the holy grail for space engineers. Today, Starlink represents the commercial realization of the Brilliant Pebbles architecture. While the payload has changed from kinetic interceptors to broadband internet routers, the engineering DNA is identical. Starlink satellites utilize laser links to pass data between satellites at the speed of light in a vacuum. This technology, essential for the mesh network envisioned for SDI to track missiles, now reduces latency for high-frequency trading and gaming. SpaceX's ability to manufacture thousands of satellites is a direct fulfillment of the industrial capacity SDIO sought to develop. Key figures such as Mike Griffin, who worked on the Brilliant Pebbles program and later served as NASA Administrator and Undersecretary of Defense, were instrumental in the early days of SpaceX. Griffin's deep understanding of the SDI architecture and his support for commercial space endeavors helped bridge the gap between Cold War concepts and Silicon Valley execution. The cycle has arguably closed with Starshield, SpaceX's dedicated government offering. Starshield leverages the Starlink architecture for secure communications and Earth observation, effectively providing the U.S. military with the resilient, global LEO layer that was first dreamed of during the height of nuclear tension.
Atoms for Peace and Profit. Advanced Materials Science. The physical demands of spaceflight are unforgiving. Materials must withstand the violent acoustic vibrations of launch, the intense heat of atmospheric re-entry, and the frigid vacuum of orbital space. To meet these challenges, Cold War scientists engineered materials with properties that did not exist in nature. Once declassified and commercialized, these supermaterials revolutionized industries ranging from medicine to professional sports. One of the most remarkable materials to emerge from the naval and aerospace research of the era is nitinol, Nickel Titanium Naval Ordnance Laboratory. Discovered in 1959 by William J. Buehler and Frederick Weng at the U.S. Naval Ordnance Laboratory, nitinol is a shape memory alloy. The researchers were searching for materials that could be used in missile nose cones to resist heat and fatigue. They accidentally discovered that a bent strip of the alloy, when heated, would snap back to its original shape with considerable force. This property is due to a reversible solid-state phase transformation between two crystal structures, martensite, the low-temperature deformable phase, and austenite, the high-temperature rigid phase. Additionally, the alloy exhibits superelasticity, the ability to undergo immense deformation and return to its original shape without permanent damage. Initially, nitinol found use in the F-14 Tomcat fighter jet as a coupling for hydraulic lines. A nitinol sleeve could be cooled, expanded, placed over a joint, and then allowed to warm up. As it attempted to return to its original, smaller shape, it clamped down on the joint, creating a seal that was impervious to the extreme vibrations of combat flight. However, the true revolution occurred when this technology migrated to medicine. In 1964, Dr. Charles Dotter, often called the father of interventional radiology, performed the first angioplasty, using a catheter to open a blocked leg artery in an 82-year-old woman who had refused amputation. While successful, early angioplasty faced the problem of the artery collapsing or narrowing again, restenosis. Nitinol provided the solution.
Its super elastic properties allowed a mesh tube, a stent, to be crushed into a tiny catheter. When deployed inside a blood vessel, the stent would self-expand to its preset shape, exerting a gentle chronic outward force to keep the vessel open. The Simon nitinol filter, 1977, was a pioneer in this field, used to trap blood clots. By the 1990s, with the refinement of the material by researchers like Cragg and Strecker, nitinol stents became the standard of care for peripheral and coronary artery disease. Today, millions of patients live with these missile cone derivatives holding their arteries open. The material also found a lucrative niche in consumer goods. In 1995, the eyewear company Marchon launched the Flexon line of eyeglass frames. Utilizing the super elasticity of nitinol, these frames could be twisted, sat upon, or crushed, and would instantly snap back to their original shape. This durability, originally engineered for the rigors of naval ordnance, solved the perennial consumer problem of broken glasses.
Carbon fiber, a material characterized by its high stiffness, high tensile strength, and low weight, is perhaps the most pervasive structural legacy of the space race. While carbon filaments had existed since Edison's light bulbs, high-performance carbon fiber was developed to solve the thermal challenges of rocket propulsion. In 1958, Dr. Roger Bacon, a scientist at Union Carbide, a major defense contractor, discovered graphite whiskers while researching the triple point of carbon. This led to the development of the Thornell line of carbon fibers. The primary military driver was the need for ablative rocket nozzles. In a solid rocket motor, the nozzle throat is subjected to temperatures that can melt tungsten. Engineers discovered that carbon-carbon composites, carbon fibers embedded in a carbon matrix, could survive this environment by slowly ablating, eroding in a controlled manner, carrying the heat away from the missile structure. This technology was critical for the Minuteman and Polaris missiles, as well as the Space Shuttle's nose cone and leading edges. The transition to civilian dominance began in 1970 when Union Carbide signed a technology exchange agreement with the Japanese firm Toray Industries. Toray perfected the use of polyacrylonitrile, PAN, as a precursor material, which allowed for the mass production of high-strength fibers. Toray aggressively marketed this space-age material to the sporting goods industry. In 1972 to 1973, the first carbon fiber fishing rods and golf shafts appeared. The material's stiffness allowed golfers to swing faster and drive the ball further. This was followed by the revolution in tennis rackets. The carbon flight and subsequent graphite rackets replaced heavy, small-headed wooden rackets. The stiffness of carbon fiber allowed for larger head sizes without warping, enabling the power baseline game that dominates modern tennis. The ultimate validation of carbon fiber in civilian engineering came in 1981, when the McLaren MP41 Formula One car debuted with a chassis made entirely of carbon fiber composites. Skeptics feared it would shatter in a crash. Instead, when driver John Watson crashed at Monza in 1981, the survival cell remained intact, proving the material's superior energy absorption capabilities. This lineage eventually led to the Boeing 780 Dreamliner, the first commercial airliner with a primary structure made of carbon fiber reinforced plastic, realizing the fuel efficiency dreams of the aerospace industry. Perhaps the most recognizable NASA invention is memory foam. In 1966, NASA commissioned Charles Yost of Stencil Aero Engineering to improve the recovery systems for the Apollo command module. Yost developed an open-cell polyurethane silicon plastic foam that possessed viscoelastic properties. It flowed like a viscous liquid under pressure, but regained its shape like an elastic solid when the pressure was removed. This temper foam was ideal for pilot seats, as it absorbed the high-energy impacts of landing and distributed the G-forces evenly across the astronaut's body, preventing pressure points. Commercialization was not immediate. the manufacturing process was difficult to control. It was not until the 1980s, when NASA released the formula to the public domain, that Fagerdala World Foams in Sweden managed to scale production. In 1991, they introduced the Tempur-Pedic mattress to the consumer market. The material that cushioned astronauts during splashdown now prevents bed sores in hospitals and provides comfort in millions of bedrooms worldwide. The Apollo program also faced a critical optical challenge. Astronauts required helmet visors that could protect them from the blinding glare of unfiltered sunlight and the abrasive impact of micrometeoroids, which travel at thousands of miles per hour. A scratch on a visor could compromise visibility during critical maneuvers or, worse, weaken the structural integrity of the helmet. NASA's Ames Research Center developed a process to deposit a thin, diamond-like carbon coating onto the plastic visors. This coating was optically transparent, but possessed a hardness comparable to glass. In 1983, the eyewear manufacturer Foster Grant licensed this technology from NASA. They combined it with their own plastics to produce Space Tech lenses that were 10 times more scratch-resistant than conventional plastic lenses. Today, virtually every pair of quality sunglasses and prescription lenses sold utilizes a derivative of this coating, a direct transfer of technology designed to withstand the harsh environment of the lunar surface.
Seeing through the clouds, weather, war, and climate. The history of satellite meteorology is inextricably linked to the history of aerial reconnaissance. In the early Cold War, the primary obstacle to gathering intelligence on the Soviet Union was not surface-to-air missiles, but clouds. A Corona spy satellite, utilizing film that had to be physically returned to Earth in a capsule, could not afford to waste frames photographing cloud tops. The National Reconnaissance Office, or NRO, needed a way to predict cloud cover over the Soviet Union with high precision to task their satellites effectively. The public face of this effort was the Television Infrared Observation Satellite Program, or TIROS. TIROS-1, launched on April 1, 1960, was the first successful weather satellite, beaming back grainy images of cloud formations that proved the utility of space-based meteorology. While TIROS was a civilian program operated by NASA, its data was immediately utilized by the military. However, the military requirements for resolution, coverage, and secrecy necessitated a dedicated system. This led to the creation of the Defense Meteorological Satellite Program, or DMSP, in the mid-1960s. DMSP was a black program, its very existence classified to avoid political fallout from the militarization of space. Operated by the U.S. Air Force, DMSP satellites, starting with Block 1 in 1962, provided the strategic weather data required to route bombers and task reconnaissance satellites. The tactical utility of this data took a dark turn during the Vietnam War. The U.S. military realized that if they could predict the weather, they might also be able to modify it. This logic gave birth to Operation Popeye, 1967 to 1972, which was a classified weather modification program conducted by the 54th Weather Reconnaissance Squadron. The objective was to make mud, not war. By seeding clouds with silver iodide over the Ho Chi Minh Trail in Laos and Vietnam, the U.S. attempted to extend the monsoon season. The goal was to wash out roads, cause landslides, and disrupt the logistical supply lines of the North Vietnamese Army. Operation Popeye relied heavily on meteorological data to identify suitable cloud formations for seeding. Over a 5-year period, more than 2,600 seeding sorties were flown.
The program remained secret until 1971, when a leak to columnist Jack Anderson led to congressional hearings. The public outcry over weather warfare resulted in the Senate adopting a resolution prohibiting the use of environmental modification techniques for hostile purposes, culminating in the Environmental Modification Convention of 1977. This episode remains a stark reminder of the dual-use nature of meteorological knowledge. The same data used to warn civilians of approaching storms was used to weaponize the rain.
The secrecy surrounding the DMSP program began to lift in 1972 when DMSP data was partially declassified to allow the civilian scientific community access to this unique resource. A further, more comprehensive declassification occurred in 1994 under the Clinton administration. These decisions unlocked a treasure trove of environmental data that has become foundational to modern climate science. One of the unique sensors aboard the DMSP satellites was the Operational Line Scan System, OLS. Designed to detect clouds by moonlight for nighttime operations, the OLS was incredibly sensitive to low levels of visible light. An unintended consequence of this sensitivity was that it captured night lights, city lights, gas flares, and fishing fleets with remarkable clarity. Economists and geographers quickly realized the value of this data. They found a strong correlation between the intensity of night lights and gross domestic product, or GDP. This luminosity data became a critical proxy for measuring economic activity in data-poor regions of the world, such as sub-Saharan Africa or closed regimes like North Korea, where official economic statistics were either non-existent or unreliable. The DMSP archive, stretching back to the 1970s, allows researchers to track urbanization, electrification, and economic growth over decades, providing an objective truth visible from orbit. Perhaps the most critical contribution of military meteorology to civilian science lies in the monitoring of the cryosphere. DMSP satellites were equipped with the Special Sensor Microwave Imager, SSMI. Unlike optical cameras, which are blocked by clouds and darkness, passive microwave sensors can see through the atmosphere to detect the microwave radiation naturally emitted by the Earth's surface. Crucially, sea ice emits a different microwave signature than open ocean water. This capability allowed scientists to monitor the extent of Arctic and Antarctic sea ice year-round, even during the long polar nights when optical satellites are blind. When combined with data from NASA's Nimbus 5 satellite, specifically the electrically scanning microwave radiometer launched in 1972, the DMSP record provides a continuous, consistent 40-plus-year baseline of sea ice extent. This dataset is the primary evidence for the rapid decline of Arctic sea ice, a key indicator of global climate change. The specific sensors designed to help nuclear submarines find gaps in the ice and bombers avoid storms are now the sentinels warning humanity of a warming planet. The modern space industry is defined by the paradigm of reusability. The sight of a Falcon 9 booster returning to Earth and landing vertically is now routine, a spectacle that has drastically lowered the cost of access to space. While SpaceX is the face of this revolution, the technological roots of VTVL lie in a largely forgotten program funded by the Strategic Defense Initiative Organization, SDIO, in the early 1990s. The DCX. In the twilight of the Cold War, SDIO sought a way to reduce the cost of launching the brilliant Pebbles constellation. The solution proposed by McDonnell Douglas was the Delta Clipper Experimental, DCXA, a single-stage-to-orbit vehicle designed to operate more like an aircraft than a missile. The DCX was a pyramid-shaped vehicle, powered by 4 hydrogen-oxygen engines,
Between 1993 and 1996, it conducted a series of flight tests at White Sands Missile Range. These tests demonstrated the core competencies required for reusability: the ability to take off, hover, translate sideways, and, crucially, land vertically on a tail-first trajectory. The program was executed with a fail-fast, fly-often philosophy that ran counter to the risk-averse culture of traditional aerospace. It operated with a skeletal ground crew and rapid turnaround times, proving that spaceflight operations could be streamlined. Despite its technical successes, the DCX program was transferred to NASA and eventually canceled in 1996 following a landing accident caused by the failure of a landing leg, a failure attributed to budget constraints that prevented the installation of ruggedized components. The DCX-A, the upgraded version, tipped over and exploded, and with it, the government's interest in VTVL waned. However, the intellectual lineage did not end. The engineers and the data from the DCX program migrated into the nascent commercial space sector. Blue Origin and SpaceX explicitly built upon the heritage of the DCX. The New Shepard vehicle of Blue Origin bears a striking resemblance to the DCX in its shape and flight profile, and many original DCX engineers found a home at Blue Origin. The hover slam, or suicide burn landing maneuver, used by the Falcon 9 of SpaceX, where the rocket engine ignites at the last second to cancel out velocity exactly at the moment of touchdown, is a direct evolution of the control logic pioneered by the Delta Clipper. The reusability that has enabled the deployment of the Starlink constellation and thus closed the loop on the SDI architecture is a technological dividend paid by the investment in the DCX.
The history of the space age is often told as a story of exploration, of footprints on the moon and rovers on Mars. However, the earthly legacy of the Cold War space race is far more intimate and pervasive. It is found in the stents that keep our arteries open, the glasses that correct our vision, the mattresses we sleep on, and the networks that carry our voices and data across the globe. The narrative arc from Sputnik to SpaceX reveals a profound transmutation of purpose. Technologies conceived for nuclear command and control, satellites, now democratize information. Materials designed for the tip of a missile, nitinol, now serve the surgeon's hand. Systems built to weaponize the weather, Operation Popeye, now provide the scientific truth of climate change, DMSP. As the world enters a new era of great power competition in space, with nations once again eyeing the high ground for strategic advantage, the lessons of the past offer a complex precedent. The military investments of today in hypersonics, nuclear thermal propulsion, and mega-constellations are likely to spawn the essential civilian infrastructures of the 22nd century. The challenge for the future is to recognize this dual-use nature early and to guide these innovations from the closed world of defense into the open commons of human progress.